not positive how well. Okay, who wants to be designated, like, secretary of this? I need, like, a volunteer. Anyone.
What does the secretary do?
Basically, if you guys ask me any questions that I don't know the answer to, which I'm sure will pop up, your job is to keep a list of those questions, and then I will go to Dr. Macedoni, and we will work at every problem that I can't solve right now, and we will get you an answer, and we will email that out to the class. So,
I'll do it.
okay.
Okay.
That's just important, just because we want to make sure that, like, you'll probably come up with questions that I just have no idea about. So, we ready to get rolling? If someone wants to close that door, that'd be awesome. Thank you. Okay. So, general information to remember, just because I think it's good to, like, kind of expect, like, how the process is going to work. It's in the testing center from this Thursday through Saturday. They're there, like, all the time, so it's not like it closes early on any of these days. Just remember those Saturday hours are limited. There's a $5 late fee if you take on Saturday. That's, like, required now because the testing center hates students. It's not timed, so feel free to take all the time you want. The average amount of time it takes students to take this is just over 2.5 hours. So, like, at minimum, block out 3. If I were you, I would block out 4. Just saying. Also, because of things like quadratic equations and having solver capabilities, if you don't have a graphing calculator, like, borrow a roommate's, borrow your wife's, like, borrow your husband's, like, get your hands on a graphing calculator. It's probably just good to do. If not, like, all the calculations can be done by hand. I just think it's a lot better if you have a better calculator. And you're allowed to use graphing calculators on this, so might as well. That being said, I did learn recently the testing center is no longer charging if you want to borrow a scientific calculator. So, but
Their calculators are really good.
one of the things also to really stress with this is we get people, and I know because I, like, grade your stuff already, we ask you questions, and you write down answers that are really good, and they involve lots of science, and they're true, but you didn't actually answer what we ask you. So, like, before you turn it in, just read through, like, literally read the question and read your answer, and, like, make sure you actually answered it. There's the necessary skills list. That's on Learning Suite under exam materials. There's a link to it. I would definitely look at that, because, like, he literally has his, like, dual monitors, and so he just, like, looks at that list, and then he writes the questions. So, if you want to know, like, it's on that list. Formula sheet, also, that's going to be a really good resource, because make sure that you can, like, go down the formula sheet and you, like, recognize when I would use this and what it's for and how to actually calculate it. And then, yeah, you're going to be fine. Like, don't worry about it too much. Like, it's just like any other class. So I sent out a Learning Suite message with a Google forum basically asking people what they wanted me to cover. So I did this in order of priority. So, like, if you responded to that, like, your stuff is getting answered first. So we're going to start with statistics. Also because I know most about statistics. Why do we use statistics in this class especially?
Numbers don't lie.
Unless you make them lie.
Yeah, it's like you can't manipulate them. But why is it super important? Like, why do we care so much? Like, real world application.
Make sure it's good data.
Yeah. So that's definitely part of it. Yeah, we want to make sure that, like, it's one thing to be correct, and it's one thing to be correct and, like, know, like, it really comes down to this idea of confidence. Like, how confident are we? Like, that's why we do analytical chemistry, is in some sense we care about all these tiny little details because we want to know for sure, like, this is what's going on. One of the things to remember is statistics only deal with random error. Like, for the scope of this class, we're always talking about, like, this Gaussian distribution, a bell curve. And so, like, systematic error, we can't really account for that. And the thing with systematic error is also you can identify systematic error and you can attempt to eliminate it, whereas random error is always going to be present. So that's why we're doing this, is to account for all the random stuff that's always just going to be a part of it. So I have up here bell curve, obviously, as you can see. That's just kind of a reminder. And then I have all these little here. So, like, this is now when you respond to me, like, what's the mean? What's the standard deviation? What's the relative standard deviation? What do all of these mean to you? And when do you use them and why? Like, you, like, literally just pick one and, like, have it in your brain. And so...
the mean is just the average of all of your data.
Okay, perfect. So you add up all your numbers, you divide it by how many number of points you have. Everyone, like, that one should feel really comfortable because you've been doing that forever and ever. Okay, standard deviations. Also Frankie.
At least the way I understand it is just kind of like the variation with your data of like how far they tend to deviate from the mean. So that's your standard deviation.
Yeah. And so that's what's being shown, right, with this. So, like, in any situation, if you're, like, more, like, if you take at least 3 standard deviations out, you should have, like, basically all of your data. So if you have, like, this super spread out data, you're collecting data points that say, like 1 milligram of iron, but also 100 milligrams of iron, we're going to be like, okay, probably not super good methodology, right? And so this is our ability to talk about variance. Relative standard deviation, how is that different? Anyone remember this formula?
You divide it by the mean, and that helps you get a feel for like what the standard deviation is when you're accounting for only the mean, I guess, like when you compare it to the mean.
Yeah, so it's just another way of expressing the standard deviation, but like focusing in on like this central, like how does the standard deviation tell me about this middle section of the graph? Degrees of freedom. And also, when would you use, like normally the problem is people get into this habit, they're like, oh, degrees of freedom, it's always n-1. That's not true. And why is that not true?
If you're doing S pooled, you have n-2, or however many. It's just
How
however
many
many,
subsets
like,
of data points?
yeah.
Yeah, so today though, like, you're working on these labs, right, and you were asked, you did the Linest function. Are your degrees of freedom 3 and not 4?
I know this, because we took the mean, which limits freedom, and then we also took the mean to create a standard deviation. So you're basically taking 2 things that limit your freedom, so you have to take 2 off.
Yeah, perfect. So the way to think about it is almost like, you almost have to think about doing an average backwards. If I gave you 5 data points and I said that the average is this, that's like a number. So if we keep that number, we keep 4 of the data points exactly the same, but we change one of them, that number though still has to be that number. Because you already like limited, it can't be a different number for that average to still be what it was. So when you're doing calculations like mean, that limits. That's why you do n-1. Then when you take standard deviation, which is based off of the mean is in the definition of standard deviation, right? So you already had to use, you already got rid of 1 degree of freedom, you also have to get rid of another degree of freedom. So it depends on how many statistics you're doing.
See where you can do an example, so hopefully I understand.
So
Does anyone think that's useful, or we can move on?
I'm trying to think. I can like specifically talk to you about that later, like if you're still asking, unless lots of people feel like that's a big issue.
Can you just maybe put it in your own words? So I would just look up the degrees of freedom. It's talking about the number of values at the end of a calculation that are free to vary.
Yeah.
What does that actually mean, that are free to vary?
So I don't know if I can, does anyone know how to operate these things? I don't do anything with this, like we can raise this
Just write on the sheet. Just kidding.
Just write on that.
I don't know, is there an arrow right there?
I'll just try and write on the small section for now. So, there we go. Okay. So what I was trying to explain earlier a bit. I can stay there. Okay. So I'm just gonna give like a small like subset of numbers, right? Right. So we have this. So if someone wants to go through, tell me what the mean is.
I'll do it real fast.
It's like this is like a trick question. I'm not a mental math person.
5.2.
Yeah.
5.2? Okay. So, perfect. So, like, this number, so then,
Standard deviation.
like, in this definition, so you went through and you were like 2 plus 5 plus 9 plus 4 plus, and then I'm just going to, like, erase this number. Like, oh no, I don't know what this is. Like, there's no ability to manipulate this anymore. Like, you don't know that this exists, but you know that there's this many values, and you know that it has to be divided by 5 in order to get this number. So, like, when you took this mean, you, like, definitively, like, sealed this in. And so no matter what you do, like, this x, like, has to be 6 in order for both of those to be true statements. Like, you can't, so, like, that's where you limit your ability to vary the data set. As soon as you take that mean, you're like, at least one of those numbers, like, even if I got rid of all these numbers, if I wanted that average, then your data point had to be 5.2. Like, that's all, like, you limit yourself to that ability.
So I see what you're saying, but I don't understand why anyone would erase the data point. Or, like, why is that
Maybe it's an
part of it?
It's not necessarily like you would intentionally do that. It's like you just don't know that value
Okay.
per se. Like, you're doing all of these calculations. So this is just a way to explain like why you effectively limit what that number can be. So like by doing these statistics, when you go and calculate a mean or a standard deviation, you are like limiting your data that it has to be a certain way. And so in order to account for that, we do the n-1, basically. And then if we were to take another statistic, it would be n-2. If you were to take another statistic that used standard deviation in it, it would be n-3. So.
Okay, so every time that we use the whole data set to do some sort of a...
Yeah, so like here we just took the average, right? And then if we were to take the standard deviation of this even like further, then you're limiting even more of these points just because like it has this cumulative effect.
So every data set that we have could have completely different degrees of freedom, just depending on what we did to it.
Yeah. So like degrees of freedom, like in terms of like just the data set, like if you do no statistics on it, like the degrees of freedom, just like all of this data set is technically 5. Like if you don't do anything.
Yeah.
Like degrees of freedom are 5, it's just n. Whereas as soon as you take a mean, then your like degrees of freedom becomes n-1. Then if you were to take the standard deviation, n-2. And that's pretty much always going to be the case. I was like trying to come up with an example of when you'd ever have more than like n-2. It's like really rare. I don't think I've ever actually come across that. So
if we were to just take the standard deviation of a data set, we would still do 2 degrees of freedom because we're using the average in order to discover.
Yeah, in order to take a standard deviation, you technically had to have taken
Even if
a
we're
mean.
not like intending like, oh, we're finding this, but we have to find this in order to find the other.
Yeah.
Okay.
So it's kind of one of those things, like, we get into this problem because we spend all this time in class working with Excel, so you're just like, great, Excel calculates the standard deviation, and then we give you a test, and we're like, actually calculate it, like, using a calculator by hand, and if you actually do that, you'd realize, like, oh, I'm taking an average, and then I'm determining it from there, so.
So we're gonna need to be able to take all these calculations by hand. That's what you're saying.
Yeah, that's what I was saying, look at the formula sheet,
Okay.
be like, I mean, I'm not saying, like,
Test and
it's not going to be a major
Okay.
component of the test, but we could give you a data set and be like, hey, like, is this, like, significantly different?
Okay.
So, also be careful with the wording of that. I mean, I know we left, like, lots of comments when we were doing, like, a lot of the statistics things. But, yeah, what you can tell using, like, hypothesis testing and F-test, it's like, you're trying to find if things are significantly different. Like, that's...
Is everything on free response on the test?
I can't actually tell you. So the reason why I'm allowed to host a review and it'll be switched for the next time is I don't actually see the test.
Okay.
So that way I'm like free to tell you like
Double-
literally
It's like a
anything.
double blind review session.
So like I could be telling you the answers and I don't know if I'm telling you all the answers right now, but like I'm going with what my best guess of like what the questions he's going to ask. Also though he said that he posted a past exam, definitely take that. Like just take it, make sure, like, even if you just, like, look at the answer key, like, while you're doing it, just make sure that if he asks any question, like, verbatim from that old test, like, guys, free points. Like, so, okay. Hopefully that made some more sense. We can try and clarify that some more, but I'm pretty sure it's mostly...
It's an actual assignment we can do first.
I'm assuming some of them is probably multiple choice, but a lot of them is probably free response. It's probably similar in like format to like reading quizzes, where it's like some multiple choice, some reading, or some free response. Okay, degrees of freedom, confidence intervals. Hopefully you feel more comfortable with those. Like again, look at the formula sheet, make sure that you can do it from there. Confidence intervals, right? We want to know how much of our data, like, can we say we're like, I'm 95%. That's always the value for this class, 95%. Confident that the actual mean, like if you were to repeat this over and over and over and over again, how many times would you get what you're proposing it, like, would the actual answer be within your confidence interval? So you basically have a number plus or minus your confidence interval, which is based off of your confidence level, so don't get those confused. CL and CI mean different things. That you're saying if I were to do this over and over and over again, like to infinity, if I were to do this exam like 95% of the time, the actual answer, like the actual true mean, which you don't know because you can't actually know that, but I am 95% confident that the actual answer is in this range. That's what that tells you.
Is there a case you can have more than, like, you can take multiple standard deviations in a measurement?
Besides pooled standard deviations?
Yeah. Or, no, just like a typical pool standard deviation.
So pooled standard deviations and things like that, like when you're comparing to see like how much like two data sets vary, then you're taking, like then you get into different statistical tests. And
Okay.
then you're just comparing. But you'd be taking the degrees of freedom from the one, the degrees of freedom of the other. And then if you were to do something like and try to merge those, then you'd probably start limiting more degrees of freedom.
Okay.
That's true. It's not projecting up here anymore. Oh, okay. Now it is. T-test, F-test, Grubbs test. Hopefully these things are familiar to you. So if anyone wants to explain the F-test, the T-test, or the Grubbs test.
Oh no, I have another question. What's the difference between confidence level and confidence interval?
So a confidence level would be the 95% confidence level, and that's what bases if you're going to find like T statistics on a student's T-test table, then you're looking at like 0.005. I think we're always doing one-tailed distributions for this class, I believe. So yeah, so like 95 is your confidence level. Your confidence interval is like the actual value you calculate using that in mind. And so as this number goes down, like if I were to say 50%, this confidence interval just got way higher because then I'm only like 50% of the time, like half the time, sure that my answer is actually in this interval. So then, wait. No, take that back, scratch that. If this goes down, if your confidence level goes up, then you can say, if I'm saying that I'm 100% sure that my value is always in here, your confidence interval would have to be huge. Just think about it that way. If you want to say that I am 100% sure that I have the possibility of being right, you would have to give literally every number. So that's why you can't have 100% confidence.
Couldn't the confidence interval be really small but still be pretty accurate if you've done enough of the sample test?
Yeah, like that's your goal, right? Is you want to be able to say that like I am positive that the answer is 2.0 plus or minus 0.00001, and that's at like 99% confidence. Like that would be awesome, because then you're like, I nailed this.
So quick to clarify, the confidence interval, is that the 95% or is that the 0.0001?
So this is your confidence level.
Okay.
So whatever number, I am this confident, that's a confidence level. Your confidence interval is the actual, like, you use this number to determine plus or minus 0.02, which is, the interval then is technically actually, it would be like the number minus 0.02 up to the number plus 0.02 is actually the interval.
Okay.
So, okay. Grubbs test, that's to determine outliers. Just make sure that you're not doing, because there's the whole, like, Q thing or whatever that you do in, like, middle school. But we're real statisticians now, so we're going to use the Grubbs test, also just because it's better. Linear regression, y equals mx plus b. This is also why I would have a graphing calculator, because I'm a very much, like, if I do a linear regression, and if you ever want someone to, like, teach you how to, like, superimpose the linear regression on your graph for a graphing calculator, you can talk to me, because I think visually it's just very helpful.
Sorry. Does he have the like, you know how there are equations that help you calculate m, b, whatever?
Mm-hmm.
Does he have that on the sheet that we're gonna have?
So, actually have, should be up here somewhere, potentially. I used to have the formula sheet. Oh, here we go. This is the actual formula sheet. So, you definitely have. So you have X bar, you have S pooled, the T statistics, the G for the Grubbs test, the confidence interval. So the mu, X bar, plus or minus, that's for that. Confidence intervals. I think more, like, when we talk about linear regression, I think it's more like we're going to give you the linear regression, we're going to ask you, like, kind of in reverse, like, what does this mean, as compared to making you calculate the linear regression, because that's just more effective. Because it takes a lot of time to actually go through and, like, do the linear regressions, per se, like, by hand, so that's my best bet there. Okay. Back to this. Okay.
So can you talk about linear regression of what it means then?
Like if we needed to do it by hand?
Sorry, I'm blanking.
Yeah. So basically, if you need to do it by hand, you would need to go through and you need to calculate out the slope. So then, like, slope, like point slope intercept form or intercept slope form, like, that's kind of just a math thing. So we're kind of hoping you already got that.
But you won't have us do like best fit line, right?
Well, so like that's when you're doing a linear regression is to get.
Well,
If you're
so
talking about
what
like an actual LSRL, then I don't think we've covered. We didn't do residuals. Okay.
I think it's in the textbook, but I don't know if you want us to memorize it.
I wouldn't be too concerned with that. I mean, it might be worth like 2 minutes of your studying, but you're like, I would focus on the ones that you've been doing like in the lab reports. Like you should be able for sure to like do the Grubbs test because outliers are a huge deal for us. Mean standard deviation, just understanding the concept behind degrees of freedom and confidence intervals, things like that. Using the t-test. I don't feel like we focused a lot on the f-test, so that's one, but it was in your book, so I wanted to make sure to include it here.
What does the f-test tell us?
The f-test is looking at differences between like two. I'm pretty sure this is where he gave the example of you have like frogs in one pond and you have frogs in another pond, and you're trying to see if those like different populations are separate from like.
I thought that was the t-test, like a two-tailed t-test.
The two-tailed t-test.
Because you test to see if it's true, and then you test to see if it's or null hypothesis on it.
Yeah, so you can do that. F-test is like a variation where you're like specifically looking at like two populations though, whereas the t-test is like you're looking whether or not like the null hypothesis is like true for that thing. So hopefully I like got you at least thinking about what you need to say for statistics, but I feel like we should kind of move on because there's a lot of other topics still to cover. So, okay. Statistics, concentration, equilibrium, all these terms should be really familiar to you because you've been doing this like through 106 and 107 and whatever other chemistry classes or also a lot of biology classes you've ever done. Concentration, equilibrium, we care about this a lot, especially because we've been doing a bunch of stuff with solutions. So molarity, molality, like hopefully we don't have to cover those, but I mean if you still need help, feel free to see us office hours, anything like that. Strong versus weak electrolytes, weight and volume percents, all those are just a lot of math and just understanding what goes on. The C1V1 equals C2V2 like dilution formula, I swear I use this all the time, so like I feel like that one's super important.
So for the weight and volume percent, so we just gonna assume that all liquids is 1 gram per milliliter?
For densities?
Yeah.
We would either give you densities or
just make that assumption.
you can only make that assumption if it's water, because it's only true for water. So.
But most of the time it's diluted into water.
Yeah. So, like, in that situation, but, I mean, if we tell you, like, oh, you're actually dissolving 0.125 iron into, like, H2SO4, the density of sulfuric acid is
You
this.
would give us that, though?
Like, yeah, we'd have to give you that value.
Because
we're not going to make you, like,
usually
memorize
same.
densities.
That's always water.
Equilibrium constants, knowing what that tells us and which side, and then Le Chatelier's principle, or if you're me in middle school, Le Chatler. Basically knowing that if we add products, like how disrupting like the concept of equilibrium, if I add something to the products, that's going to push it in the reverse way, into the reverse reaction towards the reactants. If I add a whole bunch of reactants, it's going to go out to products. It's always going to want to maintain equilibrium. Again, so these should be pretty familiar, so hopefully that's good. Acids and bases, obviously important because you did like 3 or so worksheets in class. My biggest hint for this is just do those worksheets. Like, just do them. And the answer keys are on Learning Suite, and then just like make sure that you absolutely understand like when they're strong, when they're weak. You know, we were talking about, the question I kind of still need to get clarification is how much of like yesterday's lecture is going to make it onto the test, but they're not even positive of that at the moment, except for like right now, because I think they're submitting the test now. But things like the isoelectric point, pH, when pH equals the pKa, things like that. I would be familiar with Kw, Ksp, Ka, Kb, all of those Ks. It's like our favorite letter in chemistry. Any questions? Knowing that an acid is going to be a proton donor, a base is going to be a proton acceptor. Understanding the differences between like conjugate acids and bases. If you have a really strong acid, its conjugate base is going to be super weak. If you have a super strong base, its conjugate acid super weak. If you have a weak one, they're also still going to be weak. It's kind of this thing, like if you have a strong acid, technically the base is like negligible. Like that's how weak it is. Any questions about acids and bases? Awesome. Okay, titrations. Woo! We love titrations. Like you've already done like 2 labs with them and you're going to do like a whole, well, I guess you've done 1 lab with them and then you'll continue to do a bunch more labs with this. But this is actually data that I've taken. This is for a polyprotic acid, H3PO4, which is what you guys started talking about yesterday in lecture. And so, what's the purpose of doing a titration?
Find the concentration of a solution or no concentration.
Of the analyte.
Okay. And it's like the easiest method, like as much as we hate doing titrations and we do them all the time, like there is no easier way to just like take something we know, take something we don't know, like the amount of time that you actually had to spend on the titration lab, like that's super small compared to how long it takes us to do it for other things that we can't titrate, right? So like that's why we still do titration, and it really is important to understand the concepts of like acids and bases, but also you can do like ideometric titrations, or this one here, we did this using not indicators, we did this using a voltmeter. So determining like, oh, if we suddenly get a giant jump in electrical impulse, that's like monitoring the reaction rate. What's the procedure for doing a titration? Someone that hasn't answered. I mean, you guys did a titration for lab 2, so don't tell me you don't know the procedure. Like, you spent 9 hours on it.
You have a known mass of something, and then you have an indicator. You add strong base or strong acid until the indicator changes color, and then that would be your endpoint that you hope is your equivalent.
And then knowing a lot of those, like, kind of just vocab words, if you want to review those, like endpoint and all of those other things. My computer likes to turn off. So just making sure, and then looking at the point. So also on this graph, like something that we don't have you do in this class, but basically if you go through, like you can find exactly where the equivalence point is by taking the derivative of it. So that's what that second plot is on there. So things like that. And then how do we analyze light? Okay, so you like, great, you added all of your titrant, whatever, it's at, like, you get to the equivalence point, you stop everything. You're like, okay, it took me 36 milliliters to get to this equivalence point. What does that mean? Like, why did I do this?
Are you saying that you want us to be able to calculate it on the exam?
Yeah, for sure. Like, so this kind of comes back to that whole, like, my emphasis on the C1, B1, C2, B2. Like, if I had this known concentration and this known volume, like, in my Erlenmeyer flask, and I had to add this volume of HCl, which is what we did in your lab, could I go back and determine the concentration? You know? Just being able to do that. Any questions about titrations? Like I said, you guys spent 9 hours in lab on this, so you should be pretty good. Lots of people in the like Google form that I sent out wanted to know about buoyancy corrections, which I find kind of funny because like they give you the equation, and I feel like there probably shouldn't be that many questions about it. But I guess I'd be interested, like, why? What concerns you about buoyancy corrections? Is it just like why we need to do them? I don't know. I was like kind of confused by. I'm like, this is the equation. It's
Yeah.
some version of this is on the equation sheet, so like don't freak out that you have to memorize it. Understanding that D, like sub W, that does not stand for density of water, that stands for density of weights, and those are the weights used to calibrate. Is generally 8 grams per milliliter for the scope of
Did
this.
they give us all of these densities then?
So this you measured on a balance, so we would have to give you that in the equation, be like, a little story problem, be like you put it on your balance, and this is the mass you got. Density of air we would give you, it's specific because we have one like Fort Provo, or we could give you like density of air on like, well it wouldn't be air, but like Mars or whatever, density of whatever fluid you exist in. Density of the weights is going to be 8 grams per milliliter, but we'd also tell you that. And then density of your object, which we would have to give you. So, like, it really is just recognizing, like, what goes into the formula. So, plug and chug, all of that good stuff. Sig figs, all the sig fig questions, that's important. Don't lose points for sig figs. Like, that's the worst. Besides, like, fraying to carry the 1, stuff like that.
Do you think that Dr. Macedonia is going to ask us more like the calculations and sig figs that we've been doing, or is he going to like push our knowledge like to the limit on sig figs?
We'll ask ourselves about logs, I'm sure.
Yeah.
Yeah.
Okay.
Question on that.
Can I ask about what?
Logs.
Logs, yeah.
Okay, that's actually a good point. So he'll push it a little bit.
Yeah,
Yeah.
So for the pH, there's a rule in the
Log.
book that says the sig figs pretty much always just 2 decimal places after it, because pH after that is so negligible, like the changes in it. So should we stick with that rule or actually calculate according to the sig fig rules? Like if we have a
So-
concentration of like 5 digits, should we put point and then 5 digits after that for the pH?
Well, it depends on.
Technically, one of the rules with sig figs, I was kind of trying to explain this to someone earlier today as you guys were working on your thing. But the thing with sig figs, right, is they come about because we actually have a physical limit to our ability to measure things. Like, the things that we use to measure things are man-made things, so we can only know them to so much certainty. And so that creates this limit. Technically, it's not improper. Like, when in doubt, I'd almost be like, always do less sig figs, because they can't technically get mad at you for reporting less sig figs, because you're basically saying, like, I'm just, like, not as certain, whereas if you start trying to put in 10 sig figs, we're going to be like, yeah, no. But the problem with that on the reverse side is if you were to round everything to, like, 1 sig fig, you're going to look like an idiot. They're going to be like, what are you doing? This isn't science. You're just, like, if you were to round it. So you want sig figs that accurately reflect, like, to the best of the abilities of what you can do, but you don't want to be like, oh, I'm awesome. So pH, I would always go with 2.
2 decimal places?
Yeah.
Okay.
2 places after the decimal?
No, like, so it'd be like 7.4,
Okay.
8.1, things like that. Also because, yeah, if you think about it being with, like, the pH is the negative log
Well, that's
of the
only one sig
concentration,
fig.
right? Like, that's going to limit that ability, because when you start involving logs, things happen. So, just remembering the rules. So, for addition, subtraction, right, there's, like, those rules. There's the multiplication, division rules. There's the log rules that we talked about in class, which are totally fair game, because we talked about them in class, so I just pull up that PowerPoint. Any questions?
So, are you saying that we typically won't end up with 1 sig fig?
Well, it depends. So, like, that reading quiz where you're counting ants, like, if you are counting in whole numbers, like, I mean, things like that, basically, yeah. Like, there are cases when you're only getting 1 sig fig. For a case like this in analytical chemistry, like, that's the whole reason why we do analytical chemistry is to get to, like, more sig figs. That's why we spend so much more money to get you analytical balances, to get that, like, one extra significant figure, right? So it's that balance between, like, overstating your ability to do accurate, precise measurements and your ability to, like, underestimate. So it really is, like, can I find the balance?
Can you do a log sig fig example?
I do a lot of for example. We only have, like, 5 minutes, but I would just say, like, we posted that worksheet on sig figs on Learning Suite, so I would just look at that. That way I can try and cover as much as I can in the last, like, 6 minutes. A lot of the stuff, though, in the middle is really easy. Traits of good scientists, this is, like, easy because you guys, like, wrote papers on, like, how to do good science, and you read all those articles. We spent so much time at the beginning, like, this should be really easy, but just, like, don't forget to at least briefly study these, because again, easy points. So, good scientists asking questions that actually have meaning, and they're doing work that's not just like, oh, it's cool that I can work with lasers. It's like, why am I doing work with lasers? It's because it's going to help someone. Unbiased, high-quality work. It's always a struggle because we want our results to work out exactly like we want them to, because we want to be good scientists and, like, fame and Nobel Prizes and all of that, but, you know, being able to accept that, like, we have limitations and we can't just cure cancer because we want to. Like, it takes work and to not just, like, falsify results. And also that ability to endure to the end. And integrity is a huge focus of this class, and so we gave you the example of Rosalind Franklin, and then I have up there Tesla, Einstein, and Madame Curie, if you wanted to know those. Units and conversions. I just put these up here kind of as a reminder. I mean, I still have them memorized. I don't think that we're going to be, like, super extreme and be like, do dimensional analysis with, like, zeptograms. Like, I don't think we're going to pull out any stunts like that. But, just basically knowing SI units also just in general, because when you're doing a lot of these formulas, like, especially when we get into, like, pressures with gases, right, you want to be in Kelvin. Like, you always want to be in, like, SI standard units. So that's just a good way to live life. For the scope of this class, so far we've basically only used, like, the mole and, like, kilograms, basically, seconds. Glassware calibrations. Anyone want to talk to me about this?
So your glassware isn't always exactly accurate. Like, if you think you dispense 10 milliliters, it might not actually be 10 milliliters. So you have to figure out what it's actually dispensing and calibrate your glassware for that.
Yep. Perfect. So that's why we're doing them. If we didn't do those calibrations, then you would be like, oh, hey, I dispensed 35 milliliters from my burette, and the rest of the world would be like, no. Just making sure that, like, there are limits to our ability to make glassware. Again, kind of goes with our limits with sig figs. And so we need to be able to actually, like, realistically represent the equipment we're using. So that's why we spend so much time doing calibrations, and we love them. They're important. How to perform good science. This, again, kind of goes back to the traits of a good scientist. You gotta address the need, you gotta form a hypothesis, design an experiment to actually answer your question, high-quality experiments, acknowledge that there's going to be some kind of bias or limitations, and, like, include all of those things. Precision versus accuracy. This one I'm, like, confident will be on the test in some form, so. Talk to me. Which one's which?
Oh, wait. Well, it says it right there. It says it underneath the...
Yeah.
Okay, never mind. It's not... Yeah. Precision's being able to have your multiple measurements, replicated measurements, be really close to each other. Accuracy is how close you are to the true value or the true measurement.
Perfect, right? So the ideal, right, is like high precision, high accuracy, and that's hard to achieve. But also, like, you individually should be very precise, especially because that's why we spend all this time to develop good lab skills.
So the key with accuracy is that the average just needs to be close to the true value, right? Because, like, for example, in your second dart there, you're nowhere near the true, like, the bullseye, but your average comes to the bullseye.
Yeah.
Is that okay?
Mm-hmm. So overall, like, what you would say, like, looking at your data as a whole, you're like, okay, because then if I'm getting that kind of a result, though, I could come back and be like, if I were to repeat this in an independent lab in Switzerland and have other people run it, they're still going to get the right results. It's just going to have a lot of scatter. So that's like getting accuracy at the expense of precision. Experimental error, just a thing to remember. Like, every measurement you take, like, literally everything you do is going to have error of some sort. Big thing is to identify whether it's systematic or if it's random. You can identify systematic error. If you, like, leave a little bubble in your burette, like, you can get rid of that. And so you should. Like, you should actively be searching to identify sources of experimental error and getting rid of them. Because, like, that's the one thing you do have control over. Random error, you don't have any control over. That's why we do all these statistics, though. And that's just, we can only be as precise as our instruments, and those are man-made, and we're just not perfect. Propagation of uncertainty. If you have not already looked at Keaton's worksheet, definitely go look at it. It's super good. I just include this picture because there's a question on there about Shar-Pei puppies, and I think it's adorable. Propagation of error, propagation of uncertainty, they mean the same thing. It's basically your ability to take, like, I take 6 measurements of a thing. Each one of those, I'm only certain, you know, every time I weigh my test tube, it's like 0.1 kilograms plus or minus whatever. And every time you do that, if you want to look at it all together, you have to have ways to average out that error for that entire sample. So just make sure to look at that worksheet, the keys with it, if you just scroll to the bottom. So I would just go through the problems like with the answer key and just feel confident about why they did what they did, but also we give you a lot of those formulas on the formula sheet if you need to actually calculate them.
Where is that? Is that under the Easter eggs thing?
It should be under Easter eggs and not on the announcements panel of Learning Suite. I know that Dr. Mastoni uploaded a link to the worksheet for this. So we talked about it very briefly in class, and they were like, yeah, we didn't actually talk about this a ton. But then the fact that Kean actually, like, Dr. Mastoni assigned him to, like, make this worksheet makes me want to believe that, like, there's a reason why we made him make that worksheet, so it's probably on the test in some form. So it's pretty simple, though. A lot of the times it's like taking the error like of each individual measurement, squaring it, adding them together, and then square rooting the whole thing. Like that's kind of the basic formula for a lot of it. So, and that just tells you that as you take more and more measurements, like each one's kind of independent, they each have their own error. How collectively can I be sure about the error for the entire thing? So, and I'm pretty sure that's it for, yeah. Like we're at the end. So we've covered all of the, like, I went through the necessary skills list. I tried to hit all the points on there. I tried to hit what people still had questions about. Definitely come see it. I have office hours on Thursday, and the test doesn't open until Thursday, so I mean, you could, like, come see me and then go take the test. Or Dr. Mastonia's office hours today, every, like, Tuesday through Thursday, 3 to 4. Keaton has office hours. They're posted. Good luck. Good luck with the exam.
There weren't any questions, Dr. There weren't any questions.
Okay.
Okay.
Well, it's also okay, I mean. Yeah.
So, but it's like, it's hard to see either way. So it's at 10, if this was at 10.04, does that mean it actually spends 10.04 or 9.96?
So a calibration curve is always like, this indication is what I say I
what I
delivered.
read, yeah.
Is like what I, so I, like, you're working with your pipette, I'm like,
Yeah.
I dispensed 10 mils,
milliliters, yeah.
and
But
this
it
is
says-
telling you, like, I dispensed 10.04 milliliters.
Okay, so it is 10.04. So, okay, that's what I thought.
So.
But then I started questioning. Like,
Yeah.
and I thought,
I know, it's little things like that, though, that trip people up, and you're like, it sucks when you're in the exam, and you're like, I should know this
so the
thing.
equation for least squares is not here.
I'll ask you.
But if we needed to calculate, for like,
And LSRL, do you have a graphing calculator?
Well,
I'm sure I do somewhere, but I
Yeah,
haven't used
okay.
it in forever because I've been using